Next, instead of looking at converting coordinate points, we're going to look at converting equations, polar and rectangular equations. So rectangular equations have x's and y's in them. Polar equations are going to have r's and thetas in them. Sometimes an equation that's really complicated to write in rectangular is actually quite easy to write in polar, and vice versa. So for example, this first one, x squared plus y squared equals 25, it's not a function. So it's actually something that's hard to deal with in rectangular. It's a circle. It's a circle with a radius 5. X squared plus y squared equals r squared. And so it's difficult to do in rectangular. It's not a function. If I'm graphing a rectangle, I have to graph it in 2 halves because they're not a function. In polar, though, because x squared plus y squared equals r squared, we have r squared equals 25. And r equals plus or minus 5. Now, since we know that r is going to just graph the same thing in reverse, if I graph a circle with radius 5, it's going to graph like this, and if I graph a circle with radius -5, it's going to graph the exact same circle like this, just going backwards along the angle. That means I don't need both of them. I'm duplicating right now and getting the circle twice, so we just choose one of them. So r equals 5 is the graph. And so that's it. Like, I can graph the circle this way. Now, Desmos actually does a lot better job of graphing things that are not functions than most calculators. So I can type in a non-function, x squared plus y squared equals 25, and we can get our circle to graph. Okay, so that's nice. Calculator would not be able to do that as easily. Now, I'm going to turn that off for a second. I can also go into my graph settings and change my grid to be a polar grid. And if I have a polar grid here, I can graph in polar with r equals 5. And I have the circle. Okay, now I don't think it will let me use them simultaneously. I'm just seeing both of those there on the same grid now. I'm looking at a polar grid, and so they are the same. 2 representations of the same thing, so we can get them to compare. And that's something that's really hard to do on any other device. So that's just another nice feature of Desmos. We can get these graphed rectangular or polar, and we can agree that hopefully the polar equation is a simpler equation to write and to work with. Just r equals 5. That's it. All right. Let's take a look at some of the other ones. Okay, so this, what is this? First of all, in linear, I'm sorry, oh, there we go. In rectangular, I meant to say, is linear and rectangular. So in rectangular, I would solve for y and say that this is, subtract the 5 over, add the y over. This is 2x minus 5. And so this is just a nice little line. Okay, easy to graph in rectangular. You could do it by hand in half a second. What would it look like if I turned it into polar? Okay, so in polar, I know that x is r cosine theta, minus y is r sine theta, equals 5. And then just like how in rectangular, y is usually solved for if you want it to be a function, in polar it's r that I would solve for. So I can solve for r here by factoring it out. R times 2 cosine theta minus sine theta equals 5. And so r would be equal to 5 divided by 2 cosine theta minus sine theta. It doesn't seem quite as elegant. The line is much more elegant than this description in polar. Let's graph them both and compare. Okay, so I'm going to close the 2 previous equations, and for the first part, I'm going to turn my grid back into rectangular, get my line to display. So this is the line y equals 2x minus 5. I could have graphed it implicitly since Desmos do that without solving for y, but that's okay. And then if I switch my view into polar view and I graph it, the r is equal to 5 divided by 2 cosine theta minus sine theta. And I have the same line. It's regraphing it again in polar. So it's not as pretty, this line is not as pretty in polar as it is in rectangular, but I can write it in polar as well. So again, we said sometimes we have something that looks better in polar coordinates than rectangular. Sometimes we have something that looks better in rectangular coordinates than polar. Okay, so these were both originally in rectangular, and we converted them into polar. Let's take a look at the reverse. These are both originally in polar. What would it look like if I converted them into rectangular? So the first one is actually quite similar to part A above. If I have r equals 4, I know that x squared plus y squared equals r squared, so equals 4 squared. And so this equation would be x squared plus y squared equals 16. So it's going to be another circle. This time the radius is just 4 instead of 5. I don't think we need to graph that one because it's so similar. What about this one? Okay, so on this one, I have to remember that r cosine theta is x. So this one is x equals 6. That's the rectangular equation for it. Now, x equals 6 is a vertical line, and vertical lines are actually quite difficult to graph on traditional calculators. Desmos can handle them. But it was originally a problem on the traditional calculators. If I graph x equals 6, there it is. Or if I graph r cosine, theta equals 6. And the line shows up again. You can see that it's right on top of the other line. So we have the same graph in two different ways, in polar and in rectangular. And so again, we have a case where in the first one, the polar equation was simpler, and in the second one, the rectangular equation is simpler. So it's going to depend completely on what the equation looks like. Now we've got another one down here. R is equal to 2 cosine theta plus 3 sine theta. This one's going to take us a little bit of work to get into rectangular coordinates. Back on the last one, because I had an r times a cosine theta, I could replace that with x. But I can't replace just cosine theta. So one of the strategies actually is to multiply both sides by r, or multiply everything by r. And so I'll have that r cosine theta and that r sine theta that I can replace. So r squared equals 2r cosine theta plus 3r sine theta. And now we have an r cosine theta that we can replace with x. We have an r sine theta that we can replace with y. And we have an r squared that we can replace with x squared plus y squared. So that's actually a big advantage of multiplying everything by r in this case. I now have direct replacements for everything. R squared is equal to x squared plus y squared equals 2 times r cosine theta is equal to x plus 3 times r sine theta is equal to y. And again, those definitions we are just pulling from our previous page where we defined r squared equals x squared plus y squared, r times sine theta is equal to y, and so forth. Those things that we converted coordinates with are the exact same equations that we're using to convert equations with in the previous page. Okay, so here's our equation. This equation is certainly not a function. I don't even know how to solve it for y. So it's something that's not represented well. So we'll start the top one. Not represented well in rectangular, represented better in polar. So let's graph it in both of those. So if I first graph it in polar, let's see what it would look like. So r squared equals 2, I'm sorry, the original. The original just had the r. Okay, so the original of r, and it had 2 cosine theta plus 3 sine theta. Okay, so what this looks like is a circle that's a little bit off center. Okay, now I could have found that out rectangularly. It didn't do it by subtracting the x on the same side, the y on the same side, and putting the square on both of those. So I would have been able to learn about it that way, but we didn't that. Instead, we find nothing. And if I type in the rectangular version, the x squared plus y squared equals 2x plus 3y. Again, we can see that we have the same circles. We've got that overlap on them, so they're the same thing again, which is good. We can represent them both. It's a circle that's not centered at the origin, which is why it's not just r equals a number. It's got to be off-centered. So it's pretty. Okay.